Right, in the next 30 minutes or so, I am intending to give you a quick introduction to EMW, to us. A very quick intro into filter testing and a little bit of a look at where filters fit together with the different standards. The main part of the presentation will be on the impact of the filters on GT performance as advertised. And assuming we have a little bit of time at the end, I will quickly drop into some European case studies, just a couple of photos from some European case studies. So a little bit about us. We're based between Frankfurt and Cologne, established 67 years ago in 1954, a third generation family run company. Manufacturing spread over 5 halls and about 15,000 square meters of filtration of manufacturing. And all of our products at this point in time are manufactured in Germany. A quick look at our markets. Local area ventilation, which is obviously becoming much more important with the situation that we live in at the moment with COVID. ATEX filters, but obviously most importantly, especially for today, is gas turbine filters. If we look at our products, our halls 2 and 3 make coalescer filters, reticulated filters, and also carbon impregnated filters, not photographed. Bag filters, pocket filters are in hall 1. Our mini pleats are in hall 4, and in hall 5 we have test labs, storage. We also manufacture HVAC filters, pond filters, and with our sister company, we make ceramic filters for metal filtration. I've been working for EMW for nearly 20 years, and I haven't aged a day since I joined them. Right then, part 1 done. And now a quick introduction into filter test standards and filter testing. Let's quick look in our test lab. This is the main test channel, and we're able to do a wide range of different tests here. Yeah, just a quick introduction. There's quite a lot of different parts to what we're able to do. The test channel you see, dust loading you're seeing at the end here. You also saw briefly the electrostatic discharge with isopropanol according to the ISO standards. We also do flat sheet testing, SEM testing, mass spectrometry testing. We have a lot of quality control as well, which is all built into this process. The key part of the testing is to get results, obviously, and these results look a little bit like this. We have on the left an F9 grade type filter, but tested according to the latest ISO standards. And on the right, we have the EN 1822 test of our E11 filter. And we can see from the central graphs there that the difference in performance is quite significant. We'll drop into that in a little bit later on. All of this testing brings us to results, and we can see this is a table of the main test standards that we use in the filtration industry. We have the EN 779 standard on the left, and it's important that we use the latest standard, which is 2012, and we can tell that it's 2012 through the letters at the beginning of that standard. The ISO 16890, which we talked about, or we briefly highlighted in the testing and also in the test report on the previous slide. We have the ASHRAE 52.2, which we know from the Middle East region and also from the US. And this spans the whole range of the EN 779 and the ISO standards, ISO 16890 standard, and also drops into the HEPA range. We have the HEPA standards, which is 1822, and also the latest ISO standard, which covers HEPA range as well. The image behind is SEM of some wet laid glass fiber media. So flying through this in double quick fashion, we move on to the impact of the filters on the GT performance, which is the main part of the show. So let's start with how filters affect the GT, and this is a sort of like pictorial show. Each of the following photos show the same compressor after 5,000 hours of operation. Let's kick off with F8, and we can see here the IGVs and the first stage of the compressor, and this and the gas turbine is using on and offline washing, and we can see clearly the effects of the washing through the wash marks on the blades and on the casing. The next is F9. Again, after 5,000 hours, we can see a far cleaner GT from just that one step up. But we will also see that the compressor is still being washed, and we will see that from this gas turbine setup that the washing is being more successful in cleaning the IGVs in the first stage vanes. But what is happening now is it's pushing the compressor fouling further into the compressor, where it becomes actually much harder to clean off. As the temperature gets higher, it gets baked on much harder. And we move to the first grade of HEPA, and we can see again we have the next step up of cleanliness. We still have offline washing being undertaken here, but we can see the level of cleanliness is far higher. And now we move to my personal favorite filter, the E11 filter, and now we have no on or offline washing, and we are seeing a level of cleanliness that is absolutely fantastic. Remember, this is after 5,000 hours of operation, and we're seeing a near completely clean GT. And because there's no on or offline washing, we can be confident that that cleanliness is repeated all the way through the gas turbine. We finish off with the holy grail, really, of air filtration, which for gas turbines, which is an E12 grade, and this is, for my standing, a completely clean gas turbine. So we now need to transfer those images into something like a performance, and how does that level of cleanliness, or that improvement in cleanliness, improve your performance? Well, to start with, let's have a little think about how we can what the gas turbine is doing, so what the filters are doing in the real world, not in the test, but in the real world. So we have to start by thinking, what is in the air? And from a bunch of different studies, Whitby in 1956, Clark et al. In 1996, and now in the ISO standard in 2016, we have a pretty clear idea of what particulate there is. And if we have a look at this table, we can see that the large particulate, 10 to 30 and 5 to 10 micron, this is responsible for 80% of all of the dust in the air by weight. But this 80% of dust by weight is taken up by less than 0.2% of the particulate number by number. So clearly, the very heavy particulate is low in number and easy to filter because it's large. Then we come to the 3 to 5 micron, and again, this takes up another 11%. So we're now at 91% of all dust by weight. It's over 3 microns in size in the air. We come to the 1 to 3 and 0 to 5, 1 to 3 and then finally 0 to 1 micron. And we can see that of the 0.1 micron particulate, only 3% by mass, but 98.5% by particle number. So pretty much all of the filtration that is being done in a gas turbine air filter house is of a very fine particle size. So to filter fine particle size, we need to select a filter. And I've picked just a few here. We showed the F8 and the F9, E10, E11 and E12 here. And it's worth remembering that on this graph, everything underneath the line is caught by the filter and everything above the line is not caught by the filter. So we have seen in the previous slides that 0 to 1 microns makes up 98% of our dust. And if we have an F8 filter, it is less than 50% efficient at stopping this particulate size. Whereas when we come up to the HEPA range, the performance is in a totally different ballpark. But the problem with HEPA is the more that we put in the way to stop the filters, the more we resist the airflow. And when we're resisting the airflow, we measure this obviously with differential pressure. And this is a negative when it comes to the filters. And again, we've taken the same range of filters as we saw before. We see our F8 and F9 at the bottom, E10, and we put in a couple of E12s here. But what we can show here is we've got two E12s, so basically the same media. But we have here on this E12 31 square meters and on this one 38. So we can see we can control this negativity by increasing the surface area. The greater the surface area, the lower the DP. And this has allowed us to bring our E11 38 square meter to be really very comparable to an F8 or F9 filter, which is allowing us to supply or provide high level filtration with little DP penalty. So we're going to do a quick analysis between theoretical analysis between an F9 filter, which you can see with the dirt on the left, and my favorite, the E11 on the right. So at EMW, we have created a dashboard, and this is a theoretical analysis. The assessment is a purely statistical assessment. We take into consideration the ISO dust. This is in the ISO standard 16890, which you can see in the middle of the screen I've just highlighted. We run a correction then. We take the PM data, which is easy to measure and also often available. The data, historic data, is available online for much of the world. So we can take that data, and we've put in here 25 micrograms per meter cubed, which is a relatively standard figure. And we can then break that down. If we then take our ISO standard and take it to 2.5, we then can break this down, this section down. We could integrate this line, or I've actually used a trapezoid area to take the area of each different channel, and we can put a figure as to how much of this 25 micrograms is on all of the different particle sizes. From there, we can then take, we put in our engine type, the number of filters, and we've done a static filter configuration here. We obviously know what the airflow is. We can calculate what the flow rate is per filter. With the operating hours, the flow per filter, and the amount of dust in the air, we know how much dust is going into the filter house per year, and we know what the efficiency of the filter is from our testing previously. And we know from this graph here and the PM 2.5 data, we're able to see how much of each particle size is present in the air, and from the efficiency, how good that particular filter is at filtering that particle size. And we're able to calculate how much dust is caught in each filter. And what is, I think, often a bit of an eye-opener is that a simple G4 filter up front is responsible in this particular configuration. This is the first configuration, the F9. We have a G4 filter followed by an F9 filter. And we can see that the first filter catches 2/3 of the dust by weight. And the second filter catches about 1/3 of the dust by weight. And what's interesting is only 75 grams of dust escapes through the final filter. But when we consider that those 75 grams of dust getting through the final filter are all in the size range, we can see here the dust getting through the first filter and the dust getting through the second filter, we can see all of the dust is in the range 0.1 to about 0.6 microns, more or less. It's dropping off quite a lot after here. We know and we can calculate that those 75 grams of dust actually will cover 18 square meters of surface area on the gas turbine. So what does that 75 grams of dust look like in the real world? Well, we've seen this photo already. We can see the contamination is significant, but certainly not as bad as the F8. If I run the same calculation with the F8, nearly 0.5 kilogram of dust gets through per year, and it's obviously a much more significant problem. But as I said earlier, compressor fouling isn't the solution, because as we can see from this photo here, the first stage blades are relatively clean, but the moment you get to the second stage and beyond, the fouling has got much more serious. And this is because the washing just isn't hitting these blades at all. So how does that affect performance? As I said, this is a theoretical analysis from data that is freely available through some work carried out by Alstom a few years ago. And we have here the degradation for the 4931 square meter. And we can see, broadly speaking, relatively standard. If we were to do no compressor washing, we would see 3 to 4% GT efficiency drop and up to 6 to 7% GT output drop. However, there's a few things to note here, that the GT output will not be as significant as this in a combined cycle, because the heat rate will have increased. So you will recover a not insignificant portion of that in the steam cycle. Also, this is showing a theoretical assessment based on no compressor washing. We would expect that after you see 1 to 1.5% drop in performance, then the compressor will be washed, and you will zigzag your way along through this cycle. Unfortunately, you're always then operating at the steepest part of the gradient of the degradation. But these figures seem, on first sight, to be quite extreme. And the question is, why don't the operators pick up on the fact that that the GT is degrading to this level? And of course, the reason for it is, in real life, you're looking at data that is much more broken up. And we have a bunch of challenges that when it comes to doing a GT analysis. We need to consider that this information that we see here, this raw data, it has to be corrected. And the GT engineer needs to consider IGV settings, ideally fully open at base load. It needs to consider temperature. Temperature is responsible for about 1% change in performance for every 1 degree Kelvin change up or down. Atmospheric pressure, relative humidity, fuel calorific value, fuel temperature, inlet pressure at bellmouth, exhaust pressure, exhaust temperature, stack back pressure. This is a complex analysis, and a detail and a good high quality GT engineer needs to be tracking this information to pull out this real world GT performance. So when we have a look at the second assessment, the E11 configuration, all the data remains the same. The PM is still 2.5. We have the same pre-filter GT. The intermediate filter GT is changed to an F8 just to reduce the DP, and there's no value in having an F9 when you've got an E11 behind. We can see that the DP here is now 311 pascals for this particular configuration, whereas 178 on the previous one. Dust holding, again, pre-filter is still catching 2/3 of the dust by weight. more dust is being let through the pre-filter, sorry, the intermediate filter at the F8, nearly 450 kilograms, sorry, 450 grams is let through the F8, but this is caught in almost completely by the E11. The amount of dust that actually gets through the 11, that quantity of dust running the same calculation would cover about 7 cubic millimeters. So we're seeing a far, far, far lower surface area of dust passing the final filter. And this gives us a much cleaner gas turbine, as we would imagine, and the performance degradation is in a totally different scale, looking at more like 0.5, 0.6% GT efficiency drop over a year with this level of contamination, and the GT output again is sort of 1% drop over a year, which is our ballpark figure and what we would expect. So coming to a natural conclusion at 2 minutes to the hour, we can see that clearly changing your GT from an F8 configuration and this level of fouling to something more like an E11 or an E12 is going to dramatically reduce your operating costs. It's also going to reduce the amount of outage work that the OEM is going to be doing. This level of cleaning, this fouling going in your cooling passages, etc., is going to be a major source of outage work. And simply on having higher filtration, especially with minimal DP penalty, is going to have a huge benefit. It's going to maintain the performance through the full operating cycle as well. And so for me, for now, to bring us nicely on time, that brings us to the first end to my presentation. Thank you very much. And if you've got any questions, please let me know. Otherwise, I can quickly show you a couple of photos of European sites.